Hi everyone, my name is Arun, and I'll be talking about spectral hypergraph sparsification. This is joint work with Aaron Sidford and Yang Liu. So before I get started, I'll talk about graph sparsification. So what is graph sparsification? Here we have a dense input graph G, and our goal is to compute a sparse output H, which preserves useful structural properties about the input graph. For some examples of this, we have cut sparsification by Bengtser and Karger from the 90s, where we ask for the output graph H to preserve the value of all cuts in the input graph up to some small multiplicative error. Alternatively, we have spectral sparsification by Spielman and Tang, where our goal is to ensure that H preserves all quadratic forms in the input up to some small multiplicative error, where a quadratic form is defined as the quantity x transpose Lx for an input vector x, where L is defined as the graph Laplacian matrix here. So in our talk, I'm going to generalize this notion of graph sparsification to hypergraph sparsification. So what is a hypergraph? A hypergraph is a collection of vertices, hyperedges, and weights, where each hyperedge is a subset of vertices in the input, and each weight is some non-negative number assigned to every hyperedge. So you could imagine this collection of subsets on this vertex set corresponds to a 4-edge hypergraph on these vertex sets here. So the main problem we solve in this talk is hypergraph sparsification, where we're given a dense hypergraph G, one with a lot of edges, and we aim to compute a sparse reweighted subhypergraph H, which preserves the so-called hypergraph energy for all vectors x. Here, the hypergraph energy function is this quantity here, where our weights are the non-negative values assigned to each hyperedge. And we want this hypergraph energy to be approximated for all test vectors x we could use. We observe that this notion of hypergraph sparsification generalizes graph sparsification, as if all edges are of size 2, the hypergraph energy exactly coincides with the graph Laplacian quadratic form. So now I'm going to summarize what we'll talk about for the rest of the talk. I'll go over some previous work in this problem. I'll talk about our main framework, which is sparsification by sampling. I'll then go over our two main technical pieces, which are sparsification by generic chaining and group leverage scores, our new notion of edge importances. And finally, I'll put everything together to get a new bound on hypergraph sparsifiers. So what's the previous work in this problem? Our goal, again, is to construct some subhypergraph H, which approximates the hypergraph energy for all test vectors. And the goal is to ensure that the sparsifier hypergraph has as few edges as possible. We want to minimize its sparsity. So this problem has been studied quite extensively over the past decade, and we have a long line of results for both cut sparsification and spectral sparsification on hypergraphs, where the sparsity bounds depend on the number of vertices, the desired error tolerance epsilon, and R, which is the rank of the hypergraph, the rank being the maximum number of vertices belonging to a hyperedge. So restricting to just the result on spectral sparsification, we have this line of progress over the past 5 years, which has led to the current state of the art, which are algorithms that construct sparsifiers, which have roughly n over epsilon to the 4 edges in the high rank case, and roughly n over epsilon squared edges in the low rank case. So what we do in this talk is improve this to an unconditional n over epsilon squared times log n log r for hypergraph sparsity. This improves upon the previous work in all parameter regimes. So this is our main theorem. Given a rank R hypergraph, we can construct a 1 plus epsilon approximate hypergraph sparsifier, which has n log r over epsilon squared edges. In addition, we give a efficient algorithm for constructing such hypergraph sparsifiers. We show that we can construct H in near linear time the input size. In addition, in a parallel result, James Lee, also in this year's STOC, achieved an independent result matching our sparsity guarantee by very similar techniques to us. So check out his paper if you're interested in alternate exposition of our techniques. Okay, so our algorithms are going to be achieved by a very standard technique, which is sparsification by random sampling. So for this, we're going to assign some sampling probability to every hyperedge in the input. We're going to change its edge weight to be 0 or W over P with some probability. And then we're going to delete all edges of weight 0 and return the resulting sparsifier. So as a quick sanity check, we observed that for any fixed vector x, the expected hypergraph energy in expectation over the resulting hypergraph sparsifier we got as output is preserving this. In other words, we have an unbiased estimator for any fixed vector x. So there's two key challenges to this technique. We want to show that not only does this work in expectation, but it actually preserves the hypergraph energy for any fixed vector x with high probability. And we also want to convert this bound that works for each vector x to a bound that works for all vectors x. And here's where our two main techniques are going to come into play. For the first, we're going to use our notion of edge importances called group leverage scores to guarantee that the sampling procedure preserves the hypergraph energy with high probability for fixed x. And to convert this for each bound to a for all bound, we're going to employ a technique known as generic chaining, which I'll talk about next. So in chaining, before we get into that, I'll talk about this by first defining some notation. Let's say we have an input hypergraph G, and let's say it has n vertices and m hyperedges. In addition, we're going to define these auxiliary functions G sub I, which basically equal the maximum pairwise difference of the vector x induced on the subset corresponding to the ith hyperedge. The reason for doing so is that we can now rewrite the hypergraph energy as follows. It's the sum of the reweighted sum of squares of the GIs. Okay, so again, our prototype algorithm is going to be sparsification by sampling. And we observe that it's not too hard to show that for any fixed vector x, this procedure preserves the hypergraph energy in expectation, and the variance of the sampling process is bounded as follows. So our main goal here is going to choose these PIs, these sampling probabilities, to be small enough such that this variance bound is compatible with Hopfing's inequality. And thus, we're able to show that with high probability for any fixed vector x, the hypergraph energy is preserved. Now, in fact, if we only cared about polynomially many x, if there's only some small number of x's we wanted this bound for, it would be immediately done by union bound. We could take Hopfing's inequality, get a polynomial failure chance, and then union bound, and then be done. Unfortunately, we want this to hold for all x, and there's infinitely many of them, and infinity is not polynomial in the input size. So we're going to need a more refined strategy to getting a result. So for this, we'll define a little bit more notation. Let B be the set of all points which have hypergraph energy less than 1. And what we'll do is for any point in B, we're going to construct a so-called chaining sequence, x0, x1, x2, etc., converging to x. The key observation is that given a chaining sequence, we can write the original hypergraph energy as this following telescoping sum. Leveraging this, we can bound the error in sampling, this difference in hypergraph energies in G and H, as the following by the triangle inequality. So what we're going to do is we're going to say that every term in the above expression, every term in the summation can be controlled separately. How do we do this? We'll assume that every xi in any chaining sequence belongs to some finite subset T sub I. There's only a finite number of choices for every xi. If we had this fact somehow, we could union bound over all possible values of this term here. There's only size of T sub n times size of T sub n plus 1 possible terms in the summation, and we control each of them by a Hopfing inequality. Union bounding gives us our resulting control. This basic approach has been followed in previous works in spectral hypergraph sparsification, and in fact, this sort of underlies all the previous state-of-the-art results. We sort of give a more fine-grained analysis of this technique. To do this, we're going to actually define something known as the chaining distance, which bounds the variance in sampling for measuring the error in the hypergraph energy of y and the hypergraph energy in z. The reason for doing so is that we can say that the probability, the nth term in the summation on the previous slide is large, can be bounded, the probability this is much larger than the hypergraph distance function, is bounded by some exponential and negative kappa squared for this via Hopfing's inequality. Therefore, the probability that this term is ever larger than this function of this multiple of the distance function is smaller than this thing by Hopfing's inequality and a union bound over all possible chaining sequences. Therefore, the main goal that we have is to find some sets T sub I which make this chaining distance small. If we're able to control this chaining distance, then we can use this resulting bound on what this term could be by Hopfing's inequality and union bound, and eventually control this quantity here we care about. So this gives us our fundamental chaining theorem. So in the chaining theorem, we have this chaining distance that's a function of our sampling probabilities, and we get that the resulting resulting sub-hypergraph sparsifier is a 1 plus order of gamma sparsifier, where gamma is defined as this quantity here. Here, this distance function represents the distance from x to the nearest point in the subset T sub n. This infimum is taken over the best possible chaining subsets we could have, where the size grows doubly exponentially. And this first term in this thing in the inside expression corresponds to a union bound over polynomially many choices for x naught. So this corresponds to the standard Hopfing controlling a polynomial number of events, and the second term corresponds to controlling the telescoping summation. Okay, so that's our main framework for using Hopfing's inequality. It now goes to see how we construct sampling probabilities for our approach. And for this, we define our new notion of group leverage scores. So how do we choose these probabilities? A main goal, a useful consideration to have, is that we want the variance of the sampling to be small. If we're able to say the variance of sampling a fixed vector x is much smaller than the hypergraph energy, then we'd be done by Hopkins inequality. Well, one way of doing this is to look at the expression for the variance and then see that if we're able to control g sub I of x by the original hypergraph energy times this multiple of the probability for all vectors x, then we can say the variance is very small. So how do we actually get this sort of constraint? We're going to use a tool from previous work called balanced weight assignments. So before we get into what balanced weight assignments is, it's going to be useful to generalize our setting slightly to this new thing called matrix hypergraphs. Where in a matrix hypergraph, we have a triple S, A, and V, where A is some k by n matrix, S is a collection of subsets of rows of A, and W and V is a collection of weights on the hyperedges. We should think of each subset of rows as corresponding to a single hyperedge. We can define our functions G and F analogously to the graph setting, and in fact, this matrix hypergraph notion exactly generalizes graph sparsifiers if A is the incidence matrix of the underlying graph. We can also use this notation to make our graphs unweighted without loss of generality. We can put our edge weights into this matrix A without really any loss. Okay, so our first observation here for our group leverage scores is that we can write our function g sub I in this variational form. We can convert this maximization over a subset to be a maximization over some weights that live on the simplex induced on that subset. Now, the point is, for any fixed value of W, this function inside is an ellipse in X. This forms some sort of ellipse, X transpose AWA X, for any fixed value of X. So the goal of a group leverage score intuitively is going to choose these weights W to make the biggest ellipse possible, intuitively. So for this, we can actually write this sort of ellipse size maximization problem as a convex optimization thing. So if W is the diagonal matrix corresponding to the weights, we can write this log det maximization problem, and this corresponds to making these W form the largest ellipse possible. This problem is very closely related to the John ellipse from convex geometry. And this problem also appeared in this previous work of Kaprilov et al., and they gave an equivalent view of this problem based on spanning trees. So for a quick observation based on this, because these weights are non-negative and give every hyperedge unit weight, we see that for any choice of W that's feasible for the problem, this quadratic form here is smaller than the original hypergraph energy. In addition, for any fixed vector W, we can bound g sub I of x by the following quantity here for any choice of a W via Cauchy-Schwarz. Using this, if we pick tau in the following way to be the maximum value of this quadratic form over hyperedges inside the ith hyperedge, we can say that g sub I of x is bounded in terms of tau I times the full hypergraph energy, using the observation from the previous slide as well. So if we use tau I as some proxy for our eventual sampling probabilities, we get sort of the condition we want to make Hoffing inequality happy. The main thing we need to do now is show that these tau i's actually sum to something reasonable. And for this, we can use the KKT conditions for optimization problem. KKT conditions, aka first order optimality, guarantee that if you have a hyperedge and then two rows inside the hyperedge, which are non-negative weights, the quadratic forms on those two rows are exactly the same. What that means is that we can say the sum of the taus is bounded by exactly n. In fact, it equals exactly n. So these tau i's correspond roughly to importances for each of the hyperedges, and these importances sum to n, which is a promising thing to do for sampling. So choosing these probabilities proportional to these taus should make this this chaining distance dx0 small, and therefore should be good enough for our ultimate chaining analysis. Okay, so before we actually go to putting everything together to get a sparsification result, I'll say a quick word on how to compute the group leverage scores. So we can compute these in polynomial time via convex optimization. However, solving the problem exactly seems to be quite difficult. It seems to be no better than cubic time. So to get around this issue, we introduced a relaxed notion called group leverage scores. And in group leverage scores, we want to compute a tuple tau and W, which have the same properties as balanced weight assignments, except we relax the taus to sum to order of n instead of exactly n. This ends up sufficing for our goals, and it turns out you can compute these group leverage scores efficiently via a simple iterative reweighting scheme. And in fact, we can compute these in near linear time in the graph setting. Okay, so finally, we're going to put everything together. And I'll sketch in this talk a quick argument that gets a bound of roughly n log cubed over epsilon squared for sparsity. So we get a stronger result in our paper, in fact, n log r over epsilon squared. And the stronger result is a bit more involved technically. We use a technique from the chaining literature called growth functionals. And while it's quite a bit more involved, the simpler bound of n log cubed is very straightforward, and it's a pretty good summary of the ideas we use in our paper. So what we'll do is we'll compute taus as these group leverage scores from the previous section, and for some oversampling parameter rho, we'll choose our sampling probabilities to be either 1/2 or 1, where it's 1/2 if the tau I is small enough, and it's 1 if the tau i's are large. Okay, so this is slightly unnatural. You might think that we might want to sample directly proportional to the PIs, to the tau i's. It turns out for our approach to work, we need the PIs to be lower bounded, because this will let us use Hofting's inequality. This doesn't actually hurt us at all, because we can iterate the bound that we get from this preliminary thing via, repeatedly having the sparsity, and this doesn't end up affecting our final guarantees. We can also note that it's possible to show that directly sampling proportional to the tau I suffices. This is the approach taken in the other paper by James Lee in this STOC. So if you want to see a more direct argument that gets this sparsity bound, see that paper. Okay, so as we recall from the previous sections, we have this chaining distance defined as follows, and our goal is to control this parameter gamma. This gamma ultimately affects the quality of a resulting sparsifier. So we have two terms here. We have this first term and this summation. We're first going to check that this first term is okay. For this first term, we note that by the guarantee of group leverage scores, g sub I of x squared is less than tau sub I times the original hypergraph energy. Therefore, the chaining distance from any point to 0 is bounded by 1 over square root rho for any vectors x which has unit hypergraph energy. So if rho is large enough, if rho is bigger than roughly log n over epsilon squared, this suffices for us to use Hofting's inequality. So this first term is non-problematic for us. So now we need to control the second term, the summation. So what we see that if the summation is actually a supremum over a sum, we can actually bound this by a sum over suprema. So in other words, we can bring the supremum inside the sum, and instead of controlling this, sum over supremum, or supremum over sum, we can control each of these terms separately via this quantity here. So we're going to bound the summation by controlling these numbers here, which are known as the entropy numbers in the literature. Okay, so how do we control these quantities? We're going to give first a very simple distance upper bound. So if you have 2 points x and y which have unit energy, we can bound the chaining distance between x and y by the following. And given this distance, we can now define an norm associated with this upper bound, z sub p, or norm sub p, and the set k sub z to be the set of all points which have p norm at most eta from a center point z. So our argument for this is going to be, given a collection of k sub z, we're going to pack as many copies of k sub b into this ball B as possible. The idea is that if we pack a lot of these such that we can't pack another copy of k sub z into this ball, doubling the radii cover the set B. And the point is, given a covering of the set k sub z, covering of the ball with these translates of sets k sub z, we can guarantee that for any 2 points inside a k sub z, the p norm distance is at most 2 eta. And by the previous slide, we know that the p norm dominates the chaining distance. So these collections have chaining distance at radius at most 2 eta, which suffices for us. So by choosing 1 point as a representative from every k sub z in this covering, we get a set which has small chaining distance to everything. So our main workhorse lemma for proving bounds on the number of sets in a greedy packing, and therefore a greedy covering, is going to be this lemma from Alone and Klartag from 2017, which says that given some vectors in Rn, which have unit norm, we can cover the unit ball, the unit Euclidean ball, with some number of subsets, p sub I, where every subset p sub I has small inner product radius with respect to any u sub j. So how do we use this? We observe that each g sub I that we have is actually a maximum over linear functions. Each g sub I is like internally the maximum over a subset of rows inside the original hypergraph. So to use this, we're going to define u sub j's as a function of our group leverage scores taus and w's. So we're going to find uj in this way. And we observe that the inner product of a sub j and x can be written as follows. So we observe that by the notion of group leverage cores we defined, the 2 norm of any u sub j is at most 1. In addition, the unit ball under this, in addition, like the quadratic form induced by A transpose WA is smaller than the hypergraph energy. So the Euclidean ball induced by A transpose WA is larger than the ball B, which is the unit ball of F sub G. So by using all these facts and using the lemma of Alon and Klartag, we're able to find k to the order 1 over eta squared sets, such that for any 2 points belonging to a set, the maximum value of G sub I is at most tau I over eta squared, or tau I eta squared. If we use this bound and choose parameters appropriately, we're able to say that these entropy numbers are bounded as follows. And now plugging in this into the chaining theorem and choosing rho appropriately, we get that the output that we end up with is a 1 plus order of epsilon sparsifier. So putting everything together, if the input has m hyperedges, we get an output which has this many hyperedges, 3m over 4 plus this n log cubed over epsilon squared. And then by bootstrapping this, by choosing epsilon appropriately and repeatedly halving the sparsity, or reducing by constant factor, we're able to get our final sparsity guarantee of n log cubed over epsilon squared for a 1 plus order of epsilon sparsifier. So that's going to roughly conclude our talk. We give an improved spectral hypergraph sparsifier, which has n log r over epsilon squared hyperedges. We give a new notion of hyperedge importances called group leverage cores. And we give a near linear time algorithm for computing group leverage cores and sampling hypergraph sparsifiers. That's all I have. Thanks.